In this video, we take a look at one of many examples of Newton's second law using FBDs. I often solve these problems in class, but in case you missed class, or if you just would like to review how we solve this problem, this video is for you. Let's take a look at it. It's number 78 in your textbook. 7650 kilogram helicopter accelerates upward at 0.8 meters per second squared while lifting a 1250 kilogram frame at a construction site, as the figure shows. What is the lift force exerted by the air on the helicopter rotors? Letter B, what is the tension in the cable that connects the frame to the helicopter? And letter C, what force does the cable exert on the helicopter? So three different questions, all relying on Newton's second law. It's often good to start with an FBD, and you can see that this picture has an FBD already started for the frame, but we might want to draw one for the helicopter as well. Let's go ahead and start this problem by considering whether or not we want to treat these objects separately and draw an FBD for both, or if we want to treat them as a system and just draw a single FBD. I want to consider both of those. So here we have a separate, and then we'll do versus a system. Let's first just start by drawing the FBD for each object separately. So for the helicopter, let's go ahead and just do that right next to these things here. We have some lift force on the rotors that we're eventually going to solve for. I mean, that's what we're looking for. And if we consider that the helicopter is in fact separate from the frame, then we will draw a weight force that's acting on the helicopter. Let's call it Fg sub h. And since the rope is also pulling down on this helicopter from that frame, then we'll draw a tension force as well. Now, this helicopter is accelerating upward, so I'm going to draw that acceleration vector off to the side. That's not a force, so we don't throw it on our FBD, but it is helpful to recognize which way that object is accelerating. Now, down here, if we take a look at the frame, we have a weight force acting on that frame. Let's call that Fg sub f, and we have a tension force that's lifting that frame upward. And it's important to notice, I do have an acceleration upward. That's the same value as the helicopter. I should have drawn that a little bit larger than this here. I'm going to clean that up here just a little bit so that my drawing is a little bit more accurate. Okay, it looks like I might even draw this frame a little bit larger here so that when I'm done, I clearly see that my forces are unbalanced in the upward direction, okay, on each of those. Important to note that these two here are third law pairs. They are interconnected forces that however hard the helicopter pulls up on the frame must pull down just as hard. So those are interlocked forces. Now, if I consider that as a system, you'll see how that sort of cancels out when we consider the two objects combined. So now we have this as a system. We have a lift force that we're still going to be calculating, and we have a weight force on the helicopter, and we have a weight force on the frame. And we notice we don't have to draw those tension forces because as a system, those two forces would in fact cancel each other out, and so we don't have to draw them on our FBD. Now, it's up to you really on which way you'd want to solve this, but for this video, I'm just going to go ahead and solve this using the system. It's just far easier to do. Part A is asking what is the lift force exerted by the air on the helicopter? Well, that's right here. Sum of the forces on the system is equal to the mass of the system times the acceleration of the system. So Newton's second law is foundational. We can apply it to pretty much any kind of macroscopic motion, and it's important to recognize that the sum of the forces on the objects in question is equal to the mass of those objects multiplied by the acceleration of those objects. So it's just the system that we're considering. We have three forces that are acting along on that system, and they are acting in different directions, so it's important that we get these signs correct. So upward positive, downward negative. And since I'm looking for the force on the lift force, I'm just going to solve that algebraically. Okay. And there we go. We could start plugging in numbers, but I want to go a little bit further here. I want to try to put in some other variables to replace these equations and see if we can simplify even further. So the lift force. mass of the system times A of the system plus, now let's see, the force due to gravity on the helicopter is the mass of the helicopter times G. And the force of the gravity on the frame is the mass of the frame times G. And if I look even closer here, I see that this is actually just mass of the helicopter, mass of the frame is in fact the mass of that system. So I might just take another step here. We don't have to do this. You might already see what it is that I'm doing. I can sort of combine that to be mass of the system times G. And yeah, we could actually pull out that common mass of the system and then multiply that by the acceleration system plus G. Interesting. It's a nice equation. It tells me that that lift force would normally just be equal to the weight if I were to cross off that acceleration of the system. If that were just hovering there, then the lift force would have to be equal to the weight of the system, because that A would be 0. If I'm accelerating at G, if I accelerate upward at 9.8 meters per second squared, which would be a heck of a ride in a helicopter, I suppose, I would have to have twice the lift force as normal, because I'm also accelerating upward at the same rate that the Earth is trying to accelerate downward, and it would be doubling the amount of lift force. In this case, I don't have that large of an acceleration. It's only 0.8 meters per second squared, but I can effectively just sort of add that to the value of G and calculate away. So mass of the system, let's see, that is 1,250 kilograms and 7,650 kilograms. Add those up and it looks to be about 8,900 kilograms. Multiplied by 0.8 plus 9.8. And when we do that math, we get about 94,340 newtons. And if we just round that to significant figures, it's about 94,000 newtons. And so there we go. We solved for the lift force on that helicopter from those rotors using the system and Newton's second law. Now part B. This is part A. Part B, I'd like to know the tension force in that cable. So one of the challenges with using this as a system is we saw that that actually canceled out over here. So it might be challenging to determine that tension force using that system. Let's go ahead and just consider something over here where we can maybe isolate the objects in question and then determine that tension force. Well, Newton's second law is valid for any kind of object that we want to look at. Let's just go ahead and focus on the frame, since it has the fewest number of forces that we need to consider. So sum of the forces on the frame is equal to the mass of the frame times the acceleration of that frame. Again, we don't often have to write those subscripts there, but it's important to see that they're able to be applied to individual objects as well. So I'm looking for the tension force. That's one of the two forces that are acting on that frame. And let's go ahead and just solve that algebraically. And just like we saw over here, we can pull out that common mass of the frame. And that would just simply be 1,250 kilograms multiplied by the 0.8 plus 9.8, 10.6 meters per second squared, just like we had over there. And for this, we get about 13,250 newtons, which we could round to 13,000 newtons. And there we go, part B solved. Letter C, what force does the cable exert on the helicopter? Now, we really don't have to do a lot of math here. We've already calculated that. Newton's third law says that if the helicopter is pulling the frame up with 13,000 newtons of force, then the frame must be pulling down on the helicopter with the same value. So part C is the exact same thing, 13,000 newtons, downward instead of upward. There we go, problem number 78 solved for you.